Welcome to DAR Tutors for Online and Home Tuition. Today, we're focusing on a key topic in IB Mathematics, Applications and Interpretation Higher Level. We will be exploring bivariate statistics, specifically the least squares regression line. By the end of this video, you will be able to define residuals, understand the principle of least squares regression, use your calculator to find and interpret the regression line, calculate and interpret the coefficient of determination, and differentiate between statistical reliability and validity. Our first topic is the least squares regression line. The problem with simply drawing a line of best fit by eye is that it's subjective. Different people will draw slightly different lines. To overcome this inconsistency, we use a formal mathematical method. This method is known as linear regression, and its most common form is the method of least squares. The goal of linear regression is to find the equation of the line that provides the best possible fit to a set of data points. This best fit is determined using a concept called a residual. A residual is the vertical distance between an observed data point and the regression line. For any given x value, the residual is the observed y value minus the predicted y value. Graphically, let's look at this. Imagine a scatter plot with several data points. The black line represents our potential regression line. Y equals ax plus b. For each point, the vertical distance from the point to the line is its residual. If the point is above the line, the residual is positive. If it's below, the residual is negative. Our objective is to minimize these distances overall. While a single residual tells us about one point's error, we need a way to measure the total error for all points. If we just sum the residuals, the positive and negative errors would cancel out, which wouldn't give us a true picture. To address this, the method of least squares minimizes the sum of the squared residuals. We call this the residual sum of squares, or SS-res. The formula for SS-res is the sum, from I equals 1 to n, of the square of the difference between yi and y hat I. Since the predicted value y hat I is a xi plus b, we are trying to find the values of a and b that make this sum as small as possible. Minimizing this quadratic expression for SS-res with respect to a and b gives us the formulas for the coefficients of the least squares regression line. The slope a is given by this first formula, and the y-intercept b is given by the second, which involves the means of x and y. You are not required to memorize or derive these for the exam. Instead, you will use your graphics calculator or a statistics package to find a and b. Let's work through an example. Suppose we have data on annual income and weekly grocery bills for several families. Here's the data. Income X is in thousands of pounds and grocery bill Y is in pounds. Our goal is to model the relationship between these two variables. First, we would construct a scatter diagram to visualize the data. We can see a general upward trend, suggesting a positive linear association. Next, we use our calculator. Enter the income values into one list and the grocery bills into another. Then use the linear regression function, typically denoted linreg. The calculator will output the values for A and B. In this case, A is approximately 4.1 teet and B is approximately 6.7. So, the equation of our least squares regression line is y equals 4.1 teet x minus 56.7. The coefficient a, the gradient, is about 4.1 teet. This gradient tells us that for every increase of 1 unit in x, which is 1,000 pounds in income, the predicted weekly grocery bill y increases by 4.18. So, on average, a family's grocery bill increases by 4.18 for every additional 1,000 pounds of income. Now that we have the regression line, we can use it to make predictions. Let's start with interpolation. Interpolation is when we use the model to predict a y value for an x value that lies within the range of our original data. For example, our income data ranged from 25 to 64,000 pounds. Let's estimate the weekly grocery bill for a family with an income of 45,000 pounds. We simply substitute x equals 45 into our regression equation. This gives us 4.1 times 45 minus 56.7, which equals 131.4. So, we expect a family with an annual income of 45,000 pounds to have a weekly grocery bill of approximately 131.40. Interpolation is generally considered reliable as long as the linear model is a good fit for the data. Next, let's look at extrapolation. Extrapolation is using the model to make predictions for X values that lie outside the range of our original data. For example, our highest income was £64,000. Let's estimate the weekly grocery bill for a family with an annual income of £95,000. Again, we substitute x equals 95 into our equation. This gives us 4.19 times now minus 56.7, which is 340.4. So we predict a weekly grocery bill of about 340,040. The key difference is reliability. The estimate made by extrapolation may not be reliable. Why? Because we are assuming the linear relationship we observed in our data continues unchanged into an area where we have no information. It's possible the relationship changes for higher incomes. Perhaps beyond a certain point, a family's grocery bill doesn't increase as much, or perhaps it increases more. The model cannot tell us this. So far, we've estimated a y value given an x value. But what if we want to estimate an x value given a y value? The regression line y equals ax plus b, also called the regression of y on x, is specifically designed to predict y from x. It minimizes vertical residuals, which are errors in y. It does not minimize horizontal residuals, which would be errors in x. Therefore, if we want to predict x from y, we must rearrange our equation. For example, let's estimate the annual income of a family whose weekly grocery bill is $100. We set y equals 100 in our equation. Solving for x, we add 56.7 to both sides to get 156.7 equals 4.1 t. Dividing by 4.1 t gives us x approximately 37.5, so we expect a family with a $100 weekly grocery bill to have an annual income of approximately $37,500. This prediction is an interpolation, and it is considered reliable because it's within the data range and there's a strong linear correlation. Now, let's turn our attention to the coefficient of determination, a crucial measure of the strength of a linear model. The coefficient of determination, denoted r², tells us what proportion of the total variation in the y variable is explained by the variation in the x variable. Let's visualize this with a new scatter diagram in 2 lines. The horizontal red line represents the mean of the y values, y bar. The vertical distance from a data point to this line represents the total variation of that point from the mean, or yi minus y bar. The black line is our regression line. The vertical distance from the data point to the regression line is the residual we've discussed, or yi minus y hat I. We can think of this as breaking down the total variation. The part explained by the model is the difference between the mean and the regression line's prediction. The unexplained part is the residual. The coefficient of determination, r², is calculated as 1 minus the ratio of the residual sum of squares to the total sum of squares. A higher r² value, closer to 1, indicates that more of the variation in y is explained by the linear relationship with x, meaning the model is a better fit. Importantly, r² is also equal to the square of Pearson's product moment correlation coefficient. Your calculator will typically give you both values. Let's revisit our income and grocery bill example to calculate and interpret r². From our previous calculation, the calculator output for the correlation coefficient r was approximately 0.895. To find the coefficient of determination, r², we simply square this value. 0.895 squared is approximately 0.801. Now, how do we interpret this? An r² value of 0.801 means that 80.1% of the variation in weekly grocery bills can be explained by the variation in annual income. The remaining 19.9% of the variation is due to other factors not accounted for in this simple linear model, such as family size, shopping habits, or other expenses. This is considered a strong fit. We've now reached the 10-minute mark. At DAR Tutors, we offer expert tuition in the IB, A-Level, and IGCSE curricula. If you're looking for personalized support, whether online or in your home, please don't hesitate to contact us. We're here to help you achieve your academic goals. Let's continue by discussing the impact of outliers. An outlier is a data point that is significantly different from other data points. Outliers can have a major influence on our regression analysis, distorting both the correlation coefficient and the regression line itself. Consider this data set about the yield of pumpkins. If we plot the data, we can see a general linear trend, but one point where X is 50 appears to be an outlier. The yield is lower than we might expect based on the amount of fertilizer. Let's calculate the statistics both with and without this outlier. With the outlier included, the correlation coefficient R is about 0.55, and the regression line is y equals 0.057x plus 1.9. If we remove the outlier, the correlation becomes much stronger at about 0.98. The regression line also changes, becoming y equals 0.07x plus 1.77. The gradient has increased. The outlier had a significant impact, weakening the perceived correlation and changing the line. Deciding whether to keep or remove an outlier is a critical step in data analysis, and often requires understanding the context of the data. Finally, let's explore residual plots, a powerful tool for checking if a linear model is appropriate. A residual plot is a scatter diagram where the horizontal axis represents the independent variable, x, and the vertical axis represents the residuals, Ri. We plot the point xy Ri for each data point for t. The pattern of the residual plot helps us assess the model. If the linear model is appropriate, the residual plot should show no obvious pattern. The residuals should be randomly scattered, forming a band around the x-axis. In other words, there should be no relationship between the x value and its residual. However, if the residual plot shows a clear pattern, such as a U-shape or a fan shape, it indicates that the linear model is not the best fit for the data. A nonlinear model might be more suitable. For example, a U-shape would suggest a quadratic model. Residual plots complement our other tools like correlation coefficients and scatter diagrams. A high R-squared alone isn't enough. We must also check the residual plot for patterns to be confident that a linear model is the right choice. Now we move on to reliability and validity. These are key concepts in statistical measurement. First, reliability. Reliability is a measure of how consistently a variable can be measured. It asks, if we repeat the experiment or measurement under the same conditions, will we get the same results? High reliability means that our measurement is consistent. There are several ways to test reliability. One is test-retest reliability, where the same test is given to the same group at 2 different times to see if the scores are consistent. A more appropriate method in many contexts is parallel forms reliability. Parallel forms reliability involves creating 2 different but statistically equivalent versions of a test or measurement. You then give both forms to the same group and check for consistency between the scores. In either case, to assess reliability, we would calculate Pearson's product moment correlation coefficient between the 2 sets of scores. A strong positive correlation, close to +1, indicates high reliability. Let's look at an example of parallel forms reliability. Imagine a teacher gives a random times tables test to their class one week, and then another random test the following week. This is an example of parallel forms reliability, as the tests are different but of the same type and difficulty. To check the test's reliability, we would calculate the Pearson's R between the week 1 scores and the week 2 scores. Here, a calculator shows that the correlation coefficient R is approximately 0.893. This value, close to 1, indicates a strong positive correlation. We can conclude that Mr. Pettigrew's times tables test is reliable. That means, overall, students who scored high one week tended to score high the next, and students who scored low tended to score low. The second major concept is validity. While reliability asks if a measurement is consistent, validity asks if it is accurate. Does it measure what it's supposed to measure? This is a more fundamental question. There are different types of validity. Content validity looks at how well a test covers the entire field of study. Criterion validity is what we will focus on for its statistical component. Criterion validity assesses how well one variable called the predictor can predict another, called the criterion. The criterion variable is an established, valid measure of the outcome we care about. For example, we might want to know if a university entrance exam is a valid predictor of a student's academic success. To measure criterion validity, we again use Pearson's correlation coefficient. We correlate the predictor variable, in this case the entrance exam score, with the criterion variable, which could be the student's final university grade point average. A high correlation, either positive or negative, meaning R close to +1 or equal 1, would indicate good criterion validity. Let's revisit our times tables test example to consider its validity. We concluded that the test was reliable because of the strong correlation between weekly results. But is it valid for assessing a student's arithmetic skills? This specific test only covers multiplication. A valid test of overall arithmetic skills should cover addition, subtraction, multiplication, and division. Because the test has this limitation, it likely lacks content validity. This highlights a critical point. A reliable test is not necessarily a valid test. Reliability is a necessary condition for validity, but not a sufficient one. In other words, you cannot have a valid test that isn't reliable, but you can have a reliable test that isn't valid. Let's summarize what we've covered today. We started with the least squares regression line, which is the line of best fit that minimizes the sum of squared residuals. We learned that while interpolation is generally reliable, extrapolation is not, because it involves predictions outside the data range. We then calculated and interpreted the coefficient of determination, r squared, as the proportion of variation in y explained by x. Finally, we distinguished between statistical reliability, which is about consistency, and statistical validity, which is about accuracy. A test must be reliable to be valid, but reliability alone doesn't guarantee validity. Now, let's practice with 5 IB-style questions. Feel free to pause the video, work through each problem, and then check your solution. Question 1. The time, in minutes, spent studying for a mathematics test and the score on the test are recorded for a group of 10 students. Here is the data. A. Use technology to find the equation of the regression line for y on x. B. Interpret the gradient of the regression line. C. Predict the test score for a student who studied for 2 hours. You can pause the video now to solve the problem. Let's go through the solution. First, for part A, we input the data into a calculator. Performing linear regression, ax plus b, gives us a equals 0.69 and b equals 41.5. So, the equation is y equals 0.69x plus 41.5. For part B, we interpret the gradient, which is 0.69. This means that for each additional minute spent studying, the predicted test score increases by 0.69 points. For part C, we need to predict the score for 2 hours of study. Since x is in minutes, we convert 2 hours to 120 minutes. Substituting x equals 120 into our equation, we get y equals 0.69 times 120 plus 41.5, which is 124.3. This prediction is an extrapolation, so its reliability is questionable, as test scores don't typically go this high. Question 2. The scatter diagram shows the number of people, x, in a group and the total cost, y, in dollars for a safari trip. A linear model is used. Pause here to solve this problem. Let's see the solution. For part A, we input the coordinates of the points into the calculator. The regression equation is y equals 47.9 x plus 190. For part B, the calculator gives the Pearson correlation coefficient, r, which is approximately 0.707. For part C, we remove the outlier, the group of 3, and recalculate r. This gives a much higher correlation coefficient, r equals 0.8999. For part D, we comment on the effect. Removing the outlier increased the correlation coefficient from 0.707 to 0.9999. This indicates that the outlier significantly weakened the perceived linear relationship between group size and cost. Without it, the correlation is nearly perfect. Question 3. A psychologist conducts an experiment to test the reliability of a memory game. Each participant plays the game twice, Game 1 and Game 2, and their score is recorded. Pause the video and work on this question. Here is the solution. For part A, Since the same test is given to the same participants at two different points in time to check for consistent scores, this is a test of test-retest reliability. For Part B, we input the Game 1 and Game 2 scores into the calculator and find Pearson's R. The result is approximately 0.992. For Part C, we look at the value of R. A correlation coefficient of 0.992 is very close to 1, indicating a very strong positive correlation between the scores on the two games. Therefore, the memory game is highly reliable. Its scores are very consistent over time. Question 4. A company claims that its new training program improves employee productivity. To test this, the company records the number of units produced per hour by 10 employees before and after the program. Pause the video and try this problem. Here is the solution. For Part A, inputting the data gives R equals 0.963, and squaring that gives R squared equals 0.927. For Part B, reliability is about consistency. Since these are the same employees taking a similar test at two different times, we're looking at test-retest reliability. The very strong positive correlation, 0.963, indicates high reliability. This means an employee who was productive before the training was likely productive after, and vice versa. For Part C, validity asks if the program measures what it's supposed to. The R-squared value of 0.927 means that 92.7% of the variation in productivity. After the training is explained by the productivity before the training. This is a very high percentage, suggesting that the training had little impact. In other words, 92.7% of the new score is just a reflection of the old score. Question 5. A researcher studies the relationship between the number of hours students spend on social media per week, X, and their average sleep per night, Y, in hours. The data for a random sample of 12 students is collected. The linear regression equation is found to be G15 plus 9.5. The coefficient of determination, R squared, is 0.81. Take a moment to solve this final problem. Let's review the solution. For Part A, the gradient is 0.5. Since it's negative, it indicates an inverse relationship. Specifically, for every additional hour a student spends on social media per week, their predicted average sleep per night decreases by 0.15 hours. For Part B, R squared is 0.81, which means 81% of the variation in average sleep per night can be explained by the variation in the number of hours spent on social media. The remaining 19% is due to other factors. For Part C, we predict sleep for a student spending 60 hours a week on social media. We substitute x equals 60 into the equation, which gives y equals 0.5. A predicted sleep of only 0.5 hours per night is extremely low and likely unrealistic. This is a severe case of extrapolation, as 60 hours a week is likely far outside the range of the original data. Therefore, the prediction is highly unreliable. Thank you for watching this DAR Tutors video. We have now covered the essentials of least squares regression, the coefficient of determination, and statistical reliability and validity, all tailored to the IB/AI/HL curriculum. We hope this has been a clear and helpful explanation. Remember, DAR Tutors offers expert personalized tuition for IB, A-Level, and IGCSE students. If you need more in-depth help, practice, or just a different perspective, please reach out to us. We're here to help you succeed.